Jumping into big idea 2, we will look at bonding in phases. We'll start out with covalent bonding, doing Lewis structures and shapes, and then we'll look at how those individual molecules exhibit intermolecular forces, LDF, dipole-dipole hydrogen bonding in covalent molecules for molecular solids and liquids. And then jumping into metallic and ionic and covalent network structures, and then rounding it out with gases, so we can look at all the different phases of matter and the type of bonding and forces that are involved in all of those. So let's get into a quick review of Lewis structures. First thing we got to remember here is how to calculate Lewis structures, how to draw molecules. Simple ones in rows 1 and 2. We can really look at their dot structures and see how many bonding electron pairs there are, and kind of match them up in a really simplistic way. But larger ones, we have to remember to count valence electrons. So when we look at a molecule like SF4, we have to remember that it has 34 valence electrons. And then if each of those 5 atoms needs 8 electrons to have an octet, a full octet, we casually call that the happiness of the molecule. We can see that we need 6 electrons there is the difference between those that need to be shared to get up to 40, and electrons get shared in sets of 2. So that would require 3 bonds. And a lot of times this quick calculation shows us how many bonds the molecule has, but SF4 has 4 atoms, so these 3 bonds won't actually cover that. This is an exception to the octet rule because of the extra d orbitals on the sulfur, so we don't worry about those 3 bonds or the 40 that we need to be have full octets. We instead focus on these 34 electrons to get our structure. So our structure, we look at sulfur in the middle. Each of the 4 fluorines is going to have 8 electrons around it, and which is only going to bring me to 32. And we notice we have 34. So planning ahead a little bit, when I draw this, my fluorine is going to have those 4 regions, the 32, and I'm going to have an extra lone pair. And I drew it this way because it helps us see this shape. And then we need all of our dots on all of the fluorines. They're a little harder to show up on this. But we get that structure there, and it is a trigonal bipyramidal electron geometry, or orbital geometry, but a seesaw molecular geometry. And that is those shapes are really important because they are the foundation for polarity. So polarity is going to have molecules with uneven electron distributions. So it's asymmetrical. The electrons kind of go to one side or the other, and we want to be able to draw dipole moments. And then things that are nonpolar have even electron distributions. Those are symmetrical. If you want to write that, that's a good one. I just wrote that too. Not what I was going for. Even electron distributions. It's symmetrical shapes in 3 dimensions. We look at something like water, and we can see that water is a very polar molecule. And with electronegativities, we get the direction of the dipole moment. Oxygen is more electronegative, so it has this partially negative charge. The hydrogen side of the molecule has this partial positive charge, and our dipole moment kind of looks like that. Molecule shape for the water is bent because it has 2 bonds, but it has 4 total domains. So our electron shape or electron geometry, electron pair arrangement, there's lots of different names for these, that is tetrahedral. So remember that every molecule has two shapes. And this is really our basis later when we get into solutions for the like dissolves like rule. Polar things will mix with other polar things. Nonpolar things will mix with other nonpolar things, but there's generally not a great attraction between polar and nonpolar things. Okay? All right. And then going along with that, we want to look at all the different possible shape arrangements. So how many domains are there? How many total electron regions are there around the different molecules? What are all the possibilities? Well, one possibility is to have two domains. And the shape we're going to get out of that is a linear shape. And it's going to be, we can get that with something like beryllium, where it's so small that it's kind of in the middle. It has covalent bonds as well. It's an exception on the small side of the octet rule. We can do that with like carbon dioxide that has the double bonds. Remember, double bonds count for one domain. These guys are sp hybridized. Two domains, linear. If we have three domains, we can get trigonal planar. Or if only two of those are bonded, we will get a bent shape. Okay, so boron is the exception on the small side that does this really well. It has 1, 2, 3 regions. It only needs those 6 electrons because it does that. It's kind of in the middle there, covalent bonding. But anything, a carbon with a double bond, you know, those can do that as well. Anything that is sp2 hybridized can do this. And then the bent shape, you take one of those bonds away, and you put a lone pair there, and you can get a bent shape out of that as well. Another domain, probably one of the most common and popular ones, is the 4 domains is going to be tetrahedral. This is like our CH4 carbon. Anything in that second row, this is our fill up. 8 valence electrons, be like the noble gases. We say isoelectric with the noble gases. But this is where we get the 8 valence electrons. So a lot of things follow this guy. Tetrahedral there, if we only have 3 of those, we will get trigonal pyramidal. Two of those, we will get a different type of bent. The angles are going to be a little different than the one that's trigonal planar bent because it's 120 degrees, 2 out of 3 versus 2 out of 4. And in 3 dimensions, remember those are 109.5. But in the bent molecules, the tetrahedral series, the angles change a little bit. The tetrahedral is going to be 109.5, but lone pairs take up more space. So the trigonal pyramidal is something like 107. And then something like water that would be bent in the tetrahedral category is 104.5. So those lone pairs actually push the bonds closer together. And then if there's only 1 out of the 4, we can say linear. Sometimes we say terminal. But just something like HCl that still has some lone pairs. Like that chlorine would have 3 other lone pairs on it. All of these guys, of course, are sp3 hybridized. And then we move on to the larger categories. We have 5 domains. And 5 is going to be trigonal bipyramidal. Okay, and these are exceptions to the octet rule. So they have generally this up and down region. If you need to think about angles, there's like a 180 there. And then they have that trigonal planar geometry in the middle. So all 5 of those come together to make the trigonal bipyramidal shape. If only 4 of those are bonds and you have one lone pair, the molecular shape is going to be seesaw, like the SF4 that we were looking at the beginning. If only 3 of those, we're going to get T-shaped. And if only 2 of those are bonds, we will get linear. And the electrons come off where they can have the most space. So the first ones we're going to want to come off are going to be these side ones, because then, even though they're 90 degrees away from the tops and the bottoms, they've got this 120-degree angles around the center. So if I take off these 3 side ones, first one here, then the second one, then the third one, we'll be left with this up and down linear shape. That's where they're coming from. So the electrons always come off where you can give them more room. Last category then, if we have 6 total domains, 6 total regions, this is where we get octahedral. And it's got the linear up and down, but then it's got the square in the middle, so 4, and it's flat. It's an actual square coming off the sides. If we only had 5 of those being bonds, we would get a square pyramid. And it doesn't matter which one you take off first, it's just twisting the molecule. Every angle in there is the same 90 degrees. Square pyramidal. And if only 4 of those were bonds, now we got to take off the opposite side. So if one's down here, the other electron pair will come off the top. We'll be left with that square center. We get square planar. And while we're not totally required to do this, because there's a little bit of debate for them anyway, once we get the extra hybridizations, we'll go back to here, if I have 5 total regions, the sp3 takes care of 4 of them. The extra ones are coming from d orbitals. That is important to know. You don't necessarily need to know the hybridization is dsp3, but that would be the 5th one. Sometimes they say sp3d. There's not quite consensus on that. And then if we add a 6th one, we would say D2 sp3 or sp3 D2. But you're not required to know this for the AP test. You're required to know that when we get more than 8, you are using d orbitals, but the hybridization is kind of a little bit of an extra thing. When we are doing these, we need to note a couple of things that we've already mentioned. Lone pairs take up more space. So this matters when you figure out which ones you need to take off. Lone pairs take up more space. And then when you have double and triple bonds, they take up 1 domain. They only count once. So that CO double bond, this is 1 region of space here. So CO2, there's only 2 regions. There's 4 bonds, but there's only 2 regions. This is a linear molecule. And then we will get into the types of bonds that are in there. You need to know that all the single bonds are sigma bonds, and then any extra double or triple bond is a pi bond. So this CO2 has 2 sigma bonds. The first one will be sigma on each one, and then the second one will be a pi bond on each one. So there's 1 of each type in each one of those bonds. And the pi bonds come from, this is really important, unhybridized, the extra leftover p orbitals. The unhybridized extra p orbitals. So there's kind of an overview of polarity and some of our shapes that we need to work with. The other thing that comes up, sometimes some of our shapes require resonance. Let's switch back to black. So a molecule like carbon dioxide, let's go through with a 2- charge here. I'm sorry, carbonate, the carbonate ion. This has 24 electrons with those extra 2, and 4 atoms requiring 8 electrons each gives me 32 to fill the octets, for a difference of 8 that need to be shared, 2 electrons per bond, so we can kind of see that this has 4 bonds. Now 4 bonds between 3 atoms tells us we have resonance. That carbon is going to be connected to those 3 oxygens, but then after we get those 3 oxygens in, we have a 4th bond that we need to put in. So where does it go? Well, it goes actually on all 3 of them. So we have to draw all 3 structures. And we need these arrows in between because those arrows tell us that it's actually an average of all of them. None of them exist. So sometimes the double bond can be up there, sometimes it's there, and sometimes it's there. But it's not really a true double bond anywhere. It's a mixture of all 3. And then of course you need to put the dots in all of these as well, but they don't show up well. To make sure you always have those 24 electrons. So if that's not really a double bond, what's happening? Well, that extra bond is delocalized, and it's everywhere at once. There are 3 single bonds there, but then that extra bond really goes everywhere. Wish that would show up better. Here we go. Let's try this. It's like it's a third in all spots. That extra bonding pair, it's really over all 4 atoms simultaneously. And these are our delocalized electrons. They can be delocalized over multiple atoms. That's what resonance is. We saw that they're all sharing pi bonds, but pi bonds between 2 things will give you a double or triple bond, but if I can get multiple pi bonds together, they all overlap and we can get delocalized electrons forming resonance structures. The reason we know that is because of bond orders. The bonds in here are calculated to be 1.3. They're 1 1/3 bonds. The strength is bigger than a single bond, but it's not as strong as a double bond. So we want to be able to talk about strength and bond energy. And the energy of this bond is between a single and a double. So we know that there aren't single and double bonds in that molecule. We know that they are resonance structures. And then the other one we have is length. So when we're comparing the length, we can actually see that our single bond, that's our bond order of 1. And then we have our carbonate bond, which is our 1 1/3. We just kind of use dash lines there for like a partial. And then carbon dioxide has those double bonds. Carbon monoxide has triple bonds. So we can actually see that the carbonate bond that we're working with here, that 1.3 bond, is actually in the middle of these. We can rank them between, these are the longest, single bonds are farther apart, and they have the least amount of energy to overcome. They have the lowest energy, and then the triple bonds get really close together. They are really short bonds, and they're very weak, or very, very strong. I'm sorry, there's 3 there. They're the strongest. And the carbonate falls right in between the single and the double bonds. It actually is in the middle. So just a quick recap then with the sigma and the pi bonds. The sigma bonds are all of our single bonds, are sigma bonds. They lie between the atoms. They exist between the atoms in the planes, and they are bonded between hybrid orbitals. Our pi bonds are double or triple. Okay, those are our double bonds or our triple bonds. The extra ones, so one of them is always sigma. The extra double or the extra two for the triple are pi bonds, and those are from unhybridized p orbitals. Those are our p orbitals, and they exist, they're not between the atoms, they're actually above and below the plane of the atom. Running out of space here. Above and below. Okay, so there's just an overview of resonance and it's a little bit more with the shapes. And that's for all of our covalent bonding and our covalent structures. When a group of covalent molecules get together, they have intermolecular forces. They can make solids and liquids with those intermolecular attractions based on their polarities. And then if they spread out, of course, we can get gases out of anything if we have enough energy in. So let's take a look at the solids and liquids portion. The second portion of Big Idea 2, we are looking at the phases, solids, liquids, and gases. Now, gases are assumed to have no interactions with one another because of the particles are so far apart. So when we talk about intermolecular forces, we're really just talking about solids and liquids. And the forces, in order for atoms and molecules to come together, there have to be forces that are holding them together. So our forces, our London dispersion forces are going to be our weakest, and then we say dipole, dipole. And quotation marks, hydrogen bonding. I guess let me put the bonding part in quotation marks, because remember, it is not a bond, it is just hydrogen bonding. Those three things make up our intermolecular forces. London dispersion forces are our nonpolar forces. Any molecules that exhibit no dipole moment will have London dispersion forces as their primary intermolecular force. We also call those induced dipole forces because it is a temporary polarity because electrons are not evenly distributed around the atom at all times. So there's a temporary fleeting polarity. And it's really easy to think about if you think about a hydrogen atom that has a proton in the middle and one electron on the outside. That is not evenly distributed, even though individual atoms, we kind of pretend that they're symmetrical and nonpolar. And when we get to London dispersion forces, we say larger molecules have more surface area and they're going to be stronger. Because if there's more surface area, they have more electrons, presumably if they're larger, and the word there is polarizable. They are more polarizable. The electrons will be more unevenly distributed. Okay, so those are London dispersion forces. Our dipole-dipole forces are just normal polar molecules. If they have dipole moments, their covalent structures, they will form polar molecules. Hydrogen bonding, they too are just polar molecules. but they're so small with the most electronegative atoms on the periodic table when we have FH bonds, NH or OH, covalent bonds in a molecule. They have the ability to make intermolecular hydrogen bonds with other molecules. Now, the bond in the molecule, that itself is not the bond. The intermolecular force would come when it was attached to another, like two HFs coming together. The inter part of that is, this is the hydrogen attraction. We call it a bond. Hydrogen attraction between the two different molecules. It's hydrogen bonding. So those are the three intermolecular forces. They exist with covalent structures. Now, nonmetals, when we talk about solids, get another section down here. When we talk about solids, we can have two different types here in this category. Normal nonmetal atoms. So if we wanted to make like neon or argon into a solid, if it was cold enough, they're not molecules, so we can't call them that. They are atomic solids. It's just solid made up of atoms. You have to be really careful with this because metals do that too. They look atomic, but it's the nonmetals here that really make up the atomic solid category. Metallic things make up metallic bonds and metallic solids, so they have a separate category. Anything else that's covalent is made up of individual molecules, so we call them molecular solids. So we're parsing words a little bit, but the molecules will have maybe London dispersion forces holding them together, but they themselves are called molecular solids. So sometimes those words are going to come up there. Atomic and molecular solids. And that is our covalent category. Now I'm going to put a big line down the middle here because those are our intermolecular forces. And on the other side of the aisle, we're going to get the intramolecular forces. Intra means within the molecule. So these aren't a collection of molecules. They get so large, they're just forming large super macromolecules. So after hydrogen bonding, we get into the metallic world. After metallic, the next strongest is ionic, and we're familiar with both of those guys. And then our final category is covalent network. Okay, so in metallic, we have just metals. If it's just made up of individual metals, we can have alloys that are collections of metals. We get metallic bonds. They are held together by, they have delocalized electrons. This is why they conduct. This is why they're malleable. Because all the electrons, they exist, we say they have a sea of electrons. All the atoms are delocalized. All the bonds are delocalized, and they bond with every other thing around it in a very free way. Ionic bonding is the one you're most familiar with, we've been doing all year. It's dictated by and large by Coulomb's law, Q1, Q2 over R. Large charges make up really strong ionic attractions, and then this is backwards from the covalent structures. Small radii get together and they form stronger attractions, because if you get charges closer, they have a stronger attraction, which we touched on a lot in the trends as well. That's backwards than the covalent structures, where we say larger substances are more polarizable. So ionic, we handle it this way. And then the covalent network structures they have covalent bonds, but they don't fit in our other categories because it's a repeating network of covalent bonds everywhere, almost as if the thing were one giant molecule. The AP examples that are very, very, very common that you just kind of need to know. We need to know SiO2, which is quartz or sand, glass. They're all kind of that same structure. We need to know diamond, which is carbon. And we need to know graphite, which is also carbon. And the difference between these two is the hybridization. So where diamond has sp3 hybridized carbons in all directions, graphite has sp2 hybridized carbons in all directions. That means they have a leftover p orbital that is not hybridized and allows for delocalized electrons. That's why graphite conducts electricity and diamond does not. And then we did mention between the layers of graphite, while one layer of graphite is a covalent network structure, it's so brittle and breaks because in between the layers they have London dispersion forces. But a single sheet of graphite is one of the strongest substances. It's a covalent network structure. Very, very hard to break. So those are some of our covalent networks. And then within that, we did a little bit extra on doping in this covalent network structures. The performance-enhancing chemicals that we're going to use to make our semiconductors. When we look at doping, we look at silicon covalent networks. They have the similar bonds as carbon, 4 in each direction. And since they have 4 valence electrons and they can bond 4 times with other silicones, and it is a semiconductor that we want to see how substituting other elements in for silicon can change the properties of that structure. One of them we're going to change is boron. If we put boron in a silicon structure in the middle instead of silicon, boron only has 3 electrons and there is missing 1. So it's missing an electron. This gives me a p-type semiconductor, and this is like a positive, we set a hole. So we just want to know what types of, if I have 3 less electrons, if I have 3, I can get a p-type, and then the n-type is if I had something substituted like nitrogen, where I had more electrons. Nitrogen has 5. So it has this extra electron that's negative, that's going to give me n-type. Okay, because it has 5 electrons. So what types of atoms can give me n-type or p-type doping in silicon semiconductors? And what that allows us to do is get extra electrons, moving charges in a system so that we can generate electricity. And then the last thing we have here is with all of our intermolecular forces, LDF, dipole-dipole, hydrogen bonding, and then our intramolecular forces, metallic, ionic, covalent network, we want to be able to rank them in terms of their melting points, their boiling points, their vapor pressure, how easily they give off gas. So melting points and boiling points are stronger is higher. Vapor pressure is related to the gas, so weaker ones give off more gas. Surface tension, strong surface tension from polar forces. And then there's a lot of other things, evaporation, viscosity, and any property is related to strength. And then later we're going to tie that into energy. Stronger forces that have these, they're harder to overcome, they have higher energies as well, because they're stronger. So that takes care of solids and liquids. And then when we get into gases, gases don't have those forces because they're so far apart, like we said before. So then we will wrap up by getting into gases. When we talk about gas laws, the most common thing that we're going to see is the ideal gas law equation, PV equals nRT. It's the pressure, volume, mole, and temperature relationship for gases. And we say that these are ideal because they have a set of conditions that they need to follow. Ideal gases, we say they have no volume. The individual particles have no volume. So whatever container space we have, we consider it empty space. It has room for the gases. Since they're so spread out, they take up no significant volume of that container. We also assume that they don't interact with one another. And that's the intermolecular forces. They have no intermolecular forces. Even if they're polar molecules, when you have water vapor, those particles don't interact with one another. They're moving too fast, so they overcome any forces that are there, and they're just not significant. We also define pressure. The pressure here gets measured as collisions between the particles and the container, not necessarily each other, but every time they collide, they put pressure on the container. And then in the ideal gas law, we measure temperature as the average kinetic energy. Now, these things are correlated to speed and size of particles. There's all these other things, but temperature actually measures the kinetic energy. So if they all have the same energy, we often say that larger things move slower to have the same energy as a smaller thing moving faster, so we can compare speeds that way. Gases can get a little bit tricky because we have mixtures. So when we get partial pressures, that word partial just means pressure. Don't get confused. It just means you have a mixture. It still means pressure. But in air, for example, we have oxygen and nitrogen. So we have a mixture. Each one has their own pressure. They're independent of the other. So we have partial pressures and total pressures. And then we also have mole fractions that can describe the mixture as well. And the number of moles of the particles, so if we did oxygen, the moles of oxygen over the moles total, it's going to be identical to the pressure of oxygen over the total pressure. Because if the volume and the temperature are the same, the gas constant's the same, the moles and the pressure will be proportional to one another if everything else is kept constant. We do have some simple gas laws in here that we can see how systems change. The pressures and volumes are inversely proportional, and then pressures and temperatures are directly proportional. So if one increases, the other increases. And then temperatures and volumes are also directly proportional. If you heat something up, it increases in volume. It heats up. The last part here of the gas laws is distribution curves, which are really common to see in a myriad of ways. But when we look at a distribution curve, the y-axis here is number of molecules. It's just a general counting number of particles. And the x-axis can be anything. It could be speeds, it could be energies, whatever. But if we have a distribution of particles, we see that we have a very wide distribution. Some are very high energy, some are very low. And this is the distribution of all of the molecules in the gas, all the different energies they have. And we read these again like a bar graph. Okay, when we have a distribution curve, we're almost looking at this as a series of infinitely small bars. They make a curve. So you can just kind of count. The higher that curve, the more particles there are at that particular energy. So here in the middle, we have a lot of particles here, a number of molecules. We have a lot of particles that have this energy, just a few of them that have low energy, and then just a few of them that have high energies. And if there were a temperature dependence here, we could say, okay, here's my temperature. If this substance were to heat up, we would get a different curve, and the curve has a little bit lower peak, but it has a wider distribution. So that's at a higher temperature. You can see on average the particles are moving faster. Some of them are still moving slow, but you have a much wider distribution. The curve has to go lower in height to have a wider distribution because it's the exact same number of particles. You can't just keep it the same height and shift it. Imagine that this point here were stationary. If you were just pulling that curve over to the right, the peak is going to go down. You can't just keep it the same. And then if we were to make it colder, you would have a much lower distribution and a much higher peak. So you could get colder things have a much lower distribution. More of them are moving slower. And that pretty much wraps up the gas laws. So we've done solids, liquids, gases, and solutions, and Lewis structures, and polarity. So big idea number 2.